Welcome everyone. Welcome to the 86th online Spintronics seminar. It is my great pleasure to introduce today's speaker. Professor Mathias Kläui is Professor of Physics at Johannes Gutenberg University Mainz. He received his PhD at the University of Cambridge, after which he joined the IBM research labs in Zurich. He was a junior group leader at the University of Constance and then became associate professor in a joint appointment between the EPFL and the PSI in Switzerland before moving to Mainz. His research focuses on nanomagnetism and spin dynamics on the nanoscale in new materials. His research covers from blue sky fundamental science to applied projects with major industrial partners. He has published more than 300 articles and given more than 200 invited talks. He's a senior member of the IEEE, a fellow of the IOP, and more recently a fellow of the American Physics Society, and has been awarded a number of prizes and scholarships. He is one of the 2020 IEEE Magnetic Society distinguished lecturers. For those of you who joined us earlier on, you probably remember that he's, I think, the fourth speaker of our online Spintronics seminar series, giving his DL speech. Since he has so many exciting results lately, we invited him to give a second talk. So Mathias, please continue with your talk.
Okay, great. So, well, firstly, of course, it's a great honor to be the first speaker to be invited again. I think I'm the first to be invited again.
Yes,
yes, and of course, you know, to keep people happy, of course, I make sure that the talk today has zero overlap with what some of you might have heard. Now it's already a year and a half ago, something like that. So, and I think I should really congratulate Kirill and Shin for putting together this seminal series. And you were really the trailblazers in these online seminar series, which have now sprung up in various places, of course, including also in Mainz. But, you know, that really made a big difference to the community. And so big thanks to all of you. Good. Yeah, so today I'm actually not going to talk about antiferromagnets at all, but I'm going to talk about topological spin structures from individual ultrafast motion to diffusion and collective crystallization of 2D lattices. And so I've put actually 6 subtopics. First, I'm going to introduce ultrafast chiral interactions, and then I'll show topologically stabilized skyrmions. That's more of an introduction tutorial type. And then I look at 2 types of dynamics. The first one is deterministic dynamics due to spin orbit torques, where we look at the Skirmian Hall effect. And then non-deterministic, actually diffusive dynamics due to thermal excitations. And I'll show you how we can use skyrmions for non-conventional logic, some new results, and finally also something new on the Skirmion lattice dynamics in 2D. So some of you might remember that previously I showed this slide. So I'm going to be very brief. Indeed, I'm one of the 2020-2021 distinguished lecturers, in addition to Masashi Shiraishi, Tim Mewis, and Bert Koopmans. And I just would like to highlight that the IEEE Magnetic Society is the largest learned society in magnetism, which does a lot of things, including publishing important journals and also organizing summer schools. And I'd just like to highlight these seminar series in addition to the spin talks, which we are on. Also the SPICE seminar series held, organized in Mainz, as well as the Petaspin seminar series in Messina. They've really been instrumental in keeping the community going. So let's start with the science. Now, ultra-fast chiral interactions. Well, what is a chiral interaction? Now, for you, those of you that are new to the field, let me just very briefly introduce this chiral exchange coupling by starting with the kind of conventional Heisenberg exchange. So the conventional Heisenberg exchange is the spin-spin interaction that couples 2 spins collinear, parallel, or antiparallel. But it does not actually prefer any direction. So typically, all of these directions are energetically degenerate. And that means that the resulting spin states have a random topology and random chirality. Now, is this a problem? Yes, it is a problem because sometimes you'd like to have a chiral domain ball like this, like where the spins, say, going from left to right, always rotate clockwise, but never counterclockwise. And the question is, can you actually achieve this by having a Heisenberg exchange? And the answer is not, because if you look at Heisenberg exchange, these 2, if you look at Heisenberg exchange, these 2 here are actually energetically degenerate. But nature has something in stock for us, which is the Dzyaloshinskii-Moriya interaction, which covers two spins in a ferromagnet by the orbit of a heavy metal layer, which is adjacent to it. And since you have the symmetry breaking at the interface, this is a chiral interaction that actually sets an orientation of two spins that are to be perpendicular. And the important thing, not just any perpendicular, but only this direction and not the other direction. So this means when you go have a combination of the Heisenberg, which prefers coplanar and collinear alignment, and the Dzyaloshinskii-Moriya interaction, which prefers a certain perpendicular orientation, then you end up with some spin canting as a compromise, meaning that when you go from left to right, the spins always rotate clockwise. And this means that this domain wall here, where you go from left to right and the spins rotate clockwise, is energetically preferred, whereas this one here, where the spins rotate counterclockwise, is energetically highly energetic, and so is not preferred. And this means that you'll end up with only such chiral domain walls with one chirality. And also, if you look at the Skermion, you end up with chiral Skermions. Now, what we set out to do here is we wanted to understand if the Heisenberg exchange and the Dzyaloshinskii-Moriya chiral exchange interaction, if the energy and time scales of the two interactions are the same. And for that, what we did is the following experiment. We start with such a striped domain phase, which has chiral domain walls. And then what we do is we hit this with a femtosecond optical pump laser, which then demagnetizes the magnetization and also leads to a loss of the chiral order. And then we measure how quickly the collinear order comes back and how quickly the chiral order in the domain walls comes back. And the method we use was pioneered in this paper here. And if you're interested, the paper came out a couple of months ago here. So now let's see what happens. So firstly, when we look at the signal, the sum signal, which essentially is the collinear order, we see that after, this is before the pulse, and after a few picoseconds, we have demagnetized it strongly. And then after some time, it actually, the signal comes back. The same holds for the chiral order, which we can probe by measuring this difference signal. Again, we start before the pulse, and then we lose chiral order, and then the chiral order comes back. So qualitatively, this looks the same. But if we now look at the quantitative difference, we see that the loss of collinear order and the loss of chiral order is on the same time scale, but the chiral order recovers more quickly. And this here is quite significant. So actually the chiral order comes back on a time scale that is like is much faster than the collinear order. And this is quite nice because it means that actually you have a chiral order that is more robust than the collinear order. So first the chiral order of the domain wall comes back before the magnetization of the domains comes back. All right, so that's just some nice experiment to show you how robust this chiral order is. So what can the chiral order do? Well, it can stabilize skyrmions. So let's have a look. What is a skyrmion? So you can argue with theoreticians many hours about what a skyrmion is. And for the sake of this presentation, a skyrmion is simply a spin structure as shown here, which you can map onto the unit sphere as shown in this animation. So this means we have at the center the magnetization pointing down, at the edge the magnetization pointing in the opposite direction. And now what you do is you actually you map this onto the unit sphere, and then you check what happens here at the equator. And now at the equator, different things can happen. You can have these so-called hedgehog skyrmions, where the magnetization actually rotates in a nail domain wall-like fashion between the inside and the outside of the skyrmion, or this chiral Bloch skyrmion, where the magnetization rotates like a Bloch wall. Or you can also have this skyrmion here, which also has a Bloch wall. And what I want to say is that all of these spin structures have the same topology as quantified by this winding number. And this winding number now denotes the topology of our skyrmion. And this is quite significant because if you have a topology of n equals 1, this is distinct from the uniformly magnetized state. And that means you cannot annihilate such a skyrmion by continuous deformation to the uniformly magnetized state. However, there are also states that have a trivial topology, such as this one here. It doesn't look so different, but it has distinctly different properties, because this one here, you can continuously deform to the uniformly magnetized state by simply tilting first everything to the left along this direction, and then everything up or everything down. And the consequence is that there is no important energy barrier to annihilate a spin structure like this bubble skyrmion, or whatever you want to call it, or bubble, whereas there is a significant energy to annihilate these. And this we have actually quantified. So here's a simulation where you see if you have such a chiral skyrmion, you apply a small field, it shrinks a little bit, but otherwise is stable. Whereas this one here, which is this bubble, which is topologically trivial, you just apply a small field downwards, and then you can continuously rotate it until it's completely gone in a continuous fashion. So this means you want to have skyrmions which have a topology that is distinct from the uniformly magnetized state. Now, this was all theory. We were experimentalists, and meanwhile, there are a lot of multi-layer structures that have been fabricated that host these chiral skyrmions, such as some early work on platinum cobalt tantalum, or iridium cobalt platinum, or now also some bigger skyrmions here in tantalum cobalt iron boron MgO. And the important thing is that all these black blobs, or yellow blobs, they all have the same topology of n equals 1. And if you're interested, down here, there are 2 reviews where we also looked at experimental realizations. Now, all of this that I've shown here, and most of the work has been done on metals. Metals are very nice. You can grow them, and there are lots of different combinations that host skyrmions, but they also have quite sizable damping. So one thing we wanted to look at is insulators, magnetic insulators. And what we found is that in these magnetic insulators, thulium iron garnet, we actually can also have sizable DMI of a very long length scale. So we have 16 nanometer thickness thick thulium iron garnet with still a sizable DMI. And that means we can also stabilize skyrmions, as shown here. And more recently, we also looked at the orbital torques to move them in this recent paper here. So if you're interested in how to very efficiently manipulate skyrmions in this thulium iron garnet, have a look at this paper here. So we can actually stabilize these skyrmions in 2D metallic as well as insulating layers. But more recently, we also went to 3D. So these are layers where we actually have a coupling of multiple layers. You see here in the Z direction. And what we've investigated is not just chiral coupling within a layer, but chiral coupling between 2 layers, so-called RKKY DMI. So this was found independently here by Amalia Fernandez-Pacheco, Russell Coburn, Elena Medvedenko, and also our group in 2 back-to-back papers in Nature Materials 2 years ago. And the interesting thing is that these chiral interlayer exchange coupling can actually lead to the stabilization of 3-dimensional chiral objects, or these magnetic globules as shown here. And so we have some results, which I cannot show yet to you, but the importance is that these might be really interesting for non-conventional computing, because if you want to emulate a brain, you have your neurons, which are connected by thousands of synapses to other neurons. And if you're in 2D, you can connect a spin structure only to 4 neighbors, on average. You know this from graph theory. So if you want to have the same interconnectivity by connecting structures from one to the other, and you want to have one structure connected with 1,000 other structures, the only way to go is 3D. All right, so now we have our skyrmions. Now we need to do something with them. So the first thing we did is we looked at Skirmian motion due to spin orbit torques. So this is something which actually was done a few years ago together with a group of Jeff Beach and Peter Fisher. And the student who was actually doing the experiment, Seung Woo, he actually drew this picture here before we did the experiment, where we wanted to make a skyrmion racetrack. So here we have our skyrmions on a racetrack, and we want to move them. And then we tried to do that experimentally, and we start with 4 skyrmions. That looks fantastic. And now we want to inject current, and we see what happens. And they kind of move. But if you look closely, you can see we start with 5 skyrmions. And after a couple of pulse injections, we end up with only 3 skyrmions. So we've lost 40% of our data. And so at the time, our industrial partner, Samsung, was not exactly impressed. So the question is, why did we lose half our data, and where's all this topological protection going? So what we found out that in theory, everything is perfect because, in theory, everything is always perfect. So if you have three skyrmions, they can move to the left or move to the right completely synchronously. They do exactly the same thing. And what is important to note, and we'll come to that later, if the current is flowing right-left, they move under some angle. Now, experimentally, one skyrmion, this yellow one, does what we expect. It moves back left and right depending on the current direction. One skyrmion, the black one here, doesn't move at all. And one skyrmion, the orange one, actually eats the black one. And so here we have two skyrmions playing Pac-Man. So you see now two skyrmions which are chasing each other. And then one skyrmion catches up with the other skyrmion, and then it eats it. And that should not happen. We should have this topological stabilization. And what you find out when you look very closely is that this first skyrmion, before it is eaten, is actually pinned. So it now stopped. So it stopped and the other one came to eat it. And we found that only pinned skyrmions can be annihilated. So one of the things that we set out to do is we wanted to reduce the pinning. And this was actually quite a feat, a lot of material science development to improve the stack, in particular going from polycrystalline cobalt to amorphous cobalt-iron boron. And then we came up with this nice material here based on cobalt-iron boron, where the student was super happy because he could move the skyrmions back and forth 50 times. And they were all there. So we went to Samsung, and our project monitor at Samsung, he said, 50 times is nice, but we need 10 to the 10 billion. So I went back to the student and told him, look, we need to actually do this 10 billion times, and note that every one of this motion is a single click on the pulse generator button. And the student said, well, 10 billion times clicking on the pulse generator, that's longer than the PhD, so we need to do something smarter. So because the velocity of the skyrmions is quite sizable, it can be hundreds of meters per second, we actually went to the synchrotron and actually did this experiment, not by hand, but by injecting the pulses with like megahertz repetition rate. And then we saw that indeed we can move these white blobs, these white skyrmions. And this is now a real-time movie, well, in reality, it's a couple of nanoseconds, where you see that these 5 skyrmions here, they move left and right, left and right. And this is actually now an image or a movie, which is an average over 10 billion repetitions. And that means that if only once the skyrmion had gotten out of sync with the pulse that we apply, we would just see gray. And the fact that we see these 5 white blobs moving left and right means 10 billion times they have moved left, right, left, right, left, right, and so on. And if you look at the velocity compared to the pulse shape of the injected pulse, you see the velocity tracks the injected pulse shape extremely well. And that's why they move completely back and right, back and forth, more than 10 to the 10 times. But also what you see is the current is actually flowing in this direction. And so the skyrmions are not moving parallel to the current. Or if you rotate this, then it looks like that. So the current is flowing right-left, but the skyrmions move under this angle, the so-called Skirmian Hall angle. Now, there was nothing new. This was predicted theoretically, and it was predicted that the Skirmian Hall angle just depends on the topology of the skyrmion as well as essentially its size. But what we found is that the Skirmian Hall angle actually depends on the velocity of the skyrmion. There was something new that was not expected from simple theory. And it was nice, this also was found in a back-to-back publication in the group of Axel Hoffmann, Wanjun Zhang, and our work. And we saw actually qualitatively similar behavior, but quantitatively it was different, and also our theories were very different. Their theory was based on pinning by Charles Reichert and the family, and our theory was based on viscous motion. And so we said, instead of arguing who's right, how about we just measure? And so what we did is we measured not only the Skirmian Hall angle in the viscous flow regime, which we had done previously, but also in the creep regime, which Wanjun Zhang and colleagues had done. And we find indeed there are 2 different slopes of the Skirmian Hall angle as a function of velocity for the 2 regimes. So there seems to be something different in the mechanism. And meanwhile, there's a number of nice papers here from Ms. Zeisler, Romy Juge, and Charles Reichert has some nice theory as well that explains this. And so let me show you what our current understanding is. Now, if you try to model this, and this is a nice collaboration with Jonathan Lilliard at Ghent University, if you model this with micromagnetic simulations on a very simple model where you have no pinning and no thermal excitations, you cannot reproduce this change of the Skirmian Hall angle with velocity. It's essentially flat. But if we introduce thermal excitations and also pinning, then we can actually see that initially there's a large slope and then there's a smaller slope for the viscous flow regime. And so the reason is that we start here with skyrmions that are round, but as we increase the velocity, the skyrmions get elongated in a direction perpendicular to the current direction. And this is leading to this change of the Skirmian Hall angle. But it's a bit more complex. You actually see not only the change of the shape of the skyrmion, but also the domain wall itself changes. So overall, we find three origins of the Skirmian Hall angle variation with speed. In the creep regime, we find that there are pinning effects, and this was put forward in the original paper here and explained by Charles Reichard. And then there are shape deformations due to the damping-like torque, as shown here, which we put forward in this recent paper. And then there are changes to the domain wall spin structure, as seen here, where here you have a domain wall that covers all the directions uniformly or isotropically, whereas here you see there's not enough blue and there's too much green, and that's then an effect due to the field-like torque. And all these effects lead to a change of the Skirmian Hall angle with velocity. Now, we've understood it, but it's still a nuisance, because if you want to make a racetrack, you want to have the skyrmions moving exactly along the direction of the current flow and not under this angle. So the question is, how can we get rid of the Skirmian Hall effect? And there are obvious solutions: antiferromagnetic skyrmions. So this was first suggested by Joe Barker and Oleg Tretyakov in this paper, and that was realized by Takaaki Dohi in Tohoku University, who is now with us, and William Legrand in Paris. And then recently, we also saw that we can have antiferromagnetic antiskyrmions in hematite. So this is an example, and if you're interested, here is the paper. So this is something which is great. You can do that. The problem has been solved. I don't go into more details here, but it's still an interesting physical question to see these different mechanisms of the Skirmian Hall angle. Okay, now coming to the next topic, this is something we stumbled on a little bit by accident, because after reducing the pinning and saying to the students, look, we need to have reliable motion. Why don't you reduce the pinning? The students did actually too well. And what they did is the following. They actually engineered the stack so that when we push the skyrmions inside, we can move the skyrmions by pushing current from right to left. You see that every pulse, they move a bit to the left, but they wiggle around. And so that's weird. So that we hadn't seen before. And what it turns out to be is that actually not only you have the displacement due to spin orbit torques, and you see they all move synchronously to the left, so it's chiral skyrmions, but we also see some thermal random dynamics. And the question was, is this diffusion? Because this was predicted to be suppressed. So then I told the students, well, how about you just switch off the current and field and see what happens? And this is what happens. So here we actually track the position of the skyrmions. And what we do is we just plot the position as the skyrmion moves around. And actually this initially was done manually by just tracking by hand the skyrmion. But now actually we use some neural network for optical pattern recognition and do some automatic tracking. So we can track thousands of skyrmions together. And this is like a really nice application of optical pattern recognition using deep neural networks. So when we now plot the distance that these skyrmions move as a function of time, we get a typical mean square displacement, which is linear in time, as shown here. And this means it's pure diffusion. So this was then published in this paper down here. And also there's a more recent paper by our colleagues from Wanjun Zheng's group. They also saw something similar. Now, Uli Novak, he's been able to reproduce this data using atomistic finite temperature calculations. And we were just wondering, for a racetrack, this is a nuisance. This is really bad. But it turns out that smart people like Daniele Pinner, Karin Everschow-Sitte, and colleagues, they actually suggested that we can use this thermal dynamics in stochastic and reservoir computing, so in non-conventional computing. And so we actually set out with them to look at that in more detail. And one of the requirements is, or one of the things you'd like to have is, you'd like to know, can you actually control this thermal dynamics? So of course it's thermal, so it's random, but you can do the following. You can break the rotational symmetry of the skyrmions by applying an in-plane field. And if you apply an in-plane field, you can actually make the skyrmion asymmetric. You can either change the topology going to n equals 0, or you can at least make it ellipsoidal. And then what we see is that at 0 millitesla applied, the mean square displacement in the x and y direction is identical within the error bars. But if we increase an in-plane field, we see that suddenly the two mean square displacements, i.e. the diffusion constants, change. We actually get a 50% faster diffusion along the long axis wire than along the short axis. So the Skermions now actually diffuse in one direction more strongly than in the other, and this was published in this paper here. And so this was actually suggested to be very useful for token-based Brownian computing, and so we set out to explore this non-conventional computing using Skirmions. So now coming to this part of the talk, which will be a little bit longer and comprise a bit of new ideas. So we would love, everyone is excited about non-conventional computing, and I'm happy to give you also my gist on what I think is interesting and what is useful. But I think in any case, I think it's some really nice experiments one can do for hardware implementations of non-conventional logic. And the first approach that I'm going to look into is stochastic computing. So this was suggested by Daniele Pinna, and we jointly worked with him and Karin Evershaw-Sitte in realizing that. And stochastic computing is a non-arithmetic way of calculation using random bit streams that is only approximative, which has progressive precision, and it's a simple way of multiplying numbers using only AND gates, but that has a problem, and that is the creation of unbiased, uncorrelated bit streams. Now, this sounds very fancy, and probably many of you didn't get any of that. Absolutely no problem. Let me explain you what it really means. So what are random bit streams? Now here, if you have a coin, you have heads or tails, gives you 50-50 chance to encode the value 0.5, 50%. You can do that by having a bit stream that comprises 50% ones and 50% zeros. So here, this bit stream 0, 1, 0, 0, 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0 is one example of a bit stream that represents 0.5 because it has 50% zeros and 50% ones. To encode, for instance, the value 0.25, 25%, you have a bit stream which comprises 25% ones and 75% zeros. So there are, of course, an unlimited number of bit streams that can actually represent this 0.25 or 0.5. Now, what can you do with it? We can feed our two bit streams, one which corresponds or represents 0.5 and the other one represents 0.25, into an AND gate. So here's our bit stream that represents 0.5, and here's one that represents 0.25. And now we make an AND gate. 0 and 0 is 0, 1 and 0 is 0, 0, 0 is 0, 0, 0 is 0, 1 and 1 is 1, and so on. And yeah, you could say, so what? Turns out, if we do this, the result is simply the multiplication of the two input numbers. So the result here is actually a bit stream which has 12.5% ones and 87.5% zeros. And that's exactly 0.5 times 0.25 is 0.125. So this is a way to multiply two numbers very efficiently. Now the problem is the following. This only works if the bit streams X and Y are uncorrelated. What does that mean? Here's an example of a bit stream that corresponds or represents 6/8 because it has 6 ones and 2 zeros. So 6/8. And this one here corresponds to 0.5, so 4/8 because there's 4 ones and 4 zeros. And now if I do the AND gate, I get the result 3/8. That's exactly correct. 6/8 times 1/2 is 3/8. Now I take two completely correlated input streams, namely 6/8 and 6/8 represented by the same bit stream. And then if I feed them into the AND gate, you also get 6/8, which is obviously wrong. So what we need to do is we need to take this bit stream here and we need to reshuffle the order of the ones and zeros. And if you do that, then you actually get approximately the correct result. And so for that, we need to have a way to reshuffle the order of the ones and zeros and make a bit stream decorrelated. And that's what we set out to do. and we wanted to build a reshuffler using thermally activated skyrmions. And here it is. This is our experimentally realized reshuffler. And so what we do is the following. We have here a Skirmian nucleation that corresponds to a logic 1. Here a Skirmian nucleation that corresponds to a logic 0. Then we do readout by imaging, chromacroscopy, and when the skyrmions enter the reshuffler chamber here, then we count it as a logic 1. And if they enter the reshuffler chamber here, we count this as a logic 0. And when they exit the chamber here, it's a logic 1 on the output stream. And if they exit the chamber here, it's a logic 1 on logic 0 on the output stream. So now let's see what happens. So here we start. So here skyrmions went through, so it's a logic 0. Then a skyrmion went through here, it's a logic 1, again 0. Now one skyrmion exited here, so we have 0. Another skyrmion exits here, we have a 0. Now a skyrmion exits here, it's a logic 1. Now another one exits here, it's a logic 0. And so you see we have an input stream comprising 1s and 0s, and we have an output stream comprising 1s and 0s. And now the important information is that the order of the 1s and 0s is very different. But since the skyrmions are topologically stabilized, they don't get annihilated. Every skyrmion that actually enters up here will eventually exit here. And every skyrmion that enters here will eventually exit here. So overall, you have on average the same number of 1s and 0s entering here and exiting here, but the order of the 1s and 0 will be different. And that's what we quantified, and we actually found out that the p-value change is negligible, so all the skyrmions that entered also exited, but the correlation is down to 11%. So this is now a way to have a decorrelation between the two streams using thermal skyrmion dynamics. And I have to say this was really, for me, a quite exciting result. And this very good operation of the Skirmian reshuffler is potentially very useful for this thermal stochastic calculation. So then this we try to make the cover page of Nature Nanotechnology, which obviously we failed, but that's still a nice picture. So I'm just going to show it anyway. All right, and now we can actually then make a device. So we do the reshuffler, and you can also combine it with an AND gate, and then we can multiply using probabilistic computing. So this is good. So this is something that we did, and we're still working on that. But another approach recently caught our attention, and that is token-based Brownian computing. Now, token-based Brownian computing is a type of stochastic computing using tokens to carry information. And the token can be even mice, can be some grain, can be anything that thermally or randomly moves. A mouse isn't really thermal motion, but it moves randomly. Or you can use skyrmions. And so what you need in order to do the logic is you need to have three parts or three components for this token-based Brownian computing, namely a hub, meaning a skyrmion can go into some position and then go out into different other other directions. So essentially where you have wires that are connected. You can have a ratchet, which is not absolutely necessary, but speeds up the computation, which lets skyrmions only pass from left to right and not right to left. And most importantly, you need to have a C-join, and a C-join is an operation where if one skyrmion comes in, nothing happens, it goes back out where it came from. But if two skyrmions meet at the C-join, they then actually start to move in different directions. So it has 4 exits and entrances, and if the two skyrmions arrive from left and right, if they arrive at the same time, they exit to the top and the bottom. If only one arrives left-right, it actually stays and leaves again left-right. But if 2 of them arrive at the same time together, they go into the perpendicular directions. And then you can build a half adder. This is a suggestion, a very classical suggestion, where you put in 2 inputs. Here, Skermion, you put in a token if you have an input 0 on the A and input 1 on the A. And here for the input B, if you have an input 0, you put in a token here. And if you have an input for the input B that is 1, you put in a token here. So you put always 2 tokens in, either one here or here, and one here or here. So you have to put one here or here and one here or here. And then you just let them thermally randomly move. And then you get out here the output of this half adder. Now this is really good, but it has a big problem. And that is we have here crossings of the lanes, which are not intersections, but the skyrmions should not actually feel each other when they cross here. So this is very difficult to make experimentally. So a very smart student of mine actually came up with a way to disentangle the motion of the skyrmions, which are entering in this input A and the skyrmions entering in the input B. And this is what we have. So here we have one, and here we have the other circuit. And here we have the input, the two inputs B, and here the two inputs A. And then we can actually operate them at the same time. And the only thing that you need is that the C-joints, which are these squares, they actually need to talk to each other. They need to communicate, but otherwise they're completely independent in terms of the magnetics. And so let me just show you the end of this. So now actually the two skyrmions have arrived here at the C-joint, and they've exited in a different direction from which they have entered initially. And I'll start that in the beginning. So now we stop. Now this is the end of it. Now we'll start again. So we'll put in here is one A0 and one is here B0. And now they're just thermally moving up, down, left, right, up, down, left, right. Now they meet at the C joint. Instead of going back down, they go both back up because they met. And now this one is gone out here. And this one here is still thinking a little bit about it. And now it's also going out here. So now this has major advantages. It's faster, because it's a shorter circuit, but also it can additionally be operated by artificial diffusion, making much faster operation. And this actually has been realized by our colleagues in Japan. So this is the group of Shishige Suzuki, where they did a hub, and they also looked at making a C-join where you can have this operation necessary to make a useful gate. So we then compared the performance of the different devices. And then what you see is that indeed our new device here performs much faster than the conventional device. And something that one has to be really careful about is the following. If you look at the probability, how long it takes for this operation, you see that on average it takes this many time steps. But of course, you can never predict how long it can take, so it can take forever, or nearly forever. So now for some real device, you eventually want to make sure that it runs. So initially just use thermal activation to make it move. But if after a certain amount of time, you still don't have a result, then we can, what we call, kick in artificial diffusion, where, for instance, by spin-orbitors or field gradients, we can move the skyrmions. We just shake them randomly, but we shake them strongly, and this then speeds up the computation rapidly. If you're interested, this was recently published, and we also have a patent which is currently under review. The disclosure has been submitted. And just we analyzed the speed for the calculation, and we found for realistic conditions, actually for thermal diffusion, typically for this half adder, it takes like, depending on the temperature, because it's an exponential process, between minutes and hours. But if we do induced diffusion, it can go down to microseconds. So we can do quite fast dynamics. All right, good. So this is all I wanted to show to you about this non-conventional skyrmion dynamics. And now finally, let me show you something which is maybe much less useful, but I think is really good fun, which is skyrmion lattice dynamics in 2D. Now, initially, we looked all at single skyrmions, but what we found is that we can actually nucleate not only single skyrmions, but also whole ensembles of skyrmions or skyrmion lattices. So this is experiments we did, and we wanted to find out, can we actually look at the ordering of these skyrmion lattices and understand something about 2D phase transitions. Now, to characterize these different lattices of skyrmions, we use the radial and pair correlation functions as shown here. And you can plot this in 2D. Then you see the first ring, which is the nearest neighbors, and the second ring, which is the next nearest neighbors. And since these are rings which are roughly isotropic, it means that you have no good ordering in the radial direction, in the angular direction. And we can also look at that in a time-resolved manner. And so here we see the pair correlation function as a function of distance for different times. And this is real time, so the Skirmian nucleation in many of these systems actually takes, let me just start that movie again. takes a couple of seconds. So we can, I don't know, okay. So we can see that here the skyrmions are nucleated, and you see, if you look very closely, that actually the first peak position here actually moves with time to higher distances. So initially, when the skyrmions are nucleated, they are nucleated at a distance that is a bit smaller than its equilibrium distance. And when it equilibrizes the lattice, the average distance goes up a little bit. So that's very nice because you can follow the crystallization process in real time. And now recently we wanted to understand how the Skermion nucleation of the lattice happens. And to understand this, we need the interaction potentials. And so to quantify the interaction potentials, we actually looked at such a device where we have skyrmions that are close to an edge and skyrmions that are far away from an edge, because we wanted to quantify both the skyrmion-skyrmion interaction potential and the skyrmion sample edge interaction potential. And this was done together with the group of Peter Wilnau in this very nice paper, which is currently under review, where we use iterative Boltzmann inversion in order to self-consistently fit this data that we see experimentally to obtain the skyrmion-skyrmion and skyrmion edge interaction potentials. And we can describe the interaction potentials either as a power law or as an exponential, where the sigma is the skyrmion distance and A is the prefactor giving you the steepness of the potential. And so now we did this iterative Boltzmann inversion, and then we find that actually fitting the skyrmion-skyrmion and the skyrmion wall G of R, then we can see that very clearly we have a different exponent. And in particular, we see a much steeper potential for the skyrmion-skyrmion interaction than for the skyrmion wall interaction. So here you see the skyrmion wall and the skyrmion-skyrmion. You see that the skyrmion-skyrmion is much steeper. And that is very interesting because it means that the interaction of a skyrmion with another skyrmion is really qualitatively different than the interaction of a skyrmion with the edge of our sample. Now, the importance of this is that this prefactor here is actually governing the type of phase transition that you have. So phase transitions in 2D are something that I had no clue about 2 years ago or 3 years ago, and which is, however, something really exciting. And if I had followed the Nobel Prizes in the last couple of years, I should have known that, of course, Koslitz, Thouless, they actually got Nobel Prize for topological phase transitions. So I learned this also, and I learned to distinguish between the liquid phase, which all of us know, which has long-range orientation and translational order, and the solid phase, which we also all know, which has so the liquid phase has no orientational and translational order, and the solid phase has both orientational and translational order. But in 2D, something else exists, and that's the hexatic phase. The hexatic phase has long-range orientational order, but not translational order. And yet you can see quite nicely, if you draw these hexagonal symmetry lines, you see that the skyrmions are all sitting on these lines, but their distances are random. And this means we have orientational order, but not translational order. And if you have the appropriate potential steepness, you can actually get for the liquid to hexatic a Koslitz, Thouless, Halpern, Nelson, Young phase transition. All right, so we set out to see if we can actually see this liquid to hexatic transition by varying the temperature of the fields and weighting. And we see that indeed we can get to samples where we have ordering that's in the hexatic phase, and we can look at the transition from the liquid phase to the hexatic phase. And the nice thing, and that I think makes this Skermion super exciting, is that we can follow the position of every atom of every Skermion, our artificial atoms, in real space and real time. And so you see here, this is the plot of the psi6 absolute value, as well as the angle of these domains. You see here, this is the amount of ordering. You see very good ordering, nearly perfect ordering. But there are also some grain boundaries where you see there are domains where the orientation is of this hexagonal lattice is in different directions. And then you can get rid of these grains and make this more monodomain, or you can also get worse ordering as seen here. But the nice thing is you can really see how in real time these skyrmions arrange themselves and how these lattices are formed. And if you wait for long enough, you get the spatial correlation function, and you can, from the algebraic decay, which you see here, you can identify that there is a clear hexatic phase, which was shown also in this paper by our colleagues here from Lausanne and Cologne. Now, they did a full phase transition, phase diagram of these phases and phase transitions, having a solid, hexatic, liquid phases and their phase transitions. And again, what I think is super exciting here, that this is a perfect playground to study phases and phase transitions in 2D, because you can study the dynamics of phase transitions by real space and real-time imaging. And that's something I think is not easily possible in other systems, because so far people have primarily been looking at thermodynamic properties, but not at the individual dynamics. And in particular, we can trigger this dynamics by, for instance, changing the size of the skyrmions by an abrupt change of the field. And so we can suddenly have quasi-particles which are only half as big, and then they melt, or you make them bigger and then they crystallize. And this, I think, is something that I find super exciting. If you're interested, there's a paper here where we wrote some ideas up. And so now finally, just one slide that also the effects of geometries, confinement in certain geometries is important. Here what we did is we looked at skyrmions in this confined geometry, and we looked at the arrangement and the dynamics of the skyrmions. And we find that if you have certain numbers of skyrmions, such as 10 skyrmions as shown here, they fit perfectly into this triangle. You see 4, 3, 2, 1 skyrmion, and they also don't move. And this just means they are happy to sit as they are. Also, if you look at 6 skyrmions, you have 3, you see now the laser pointer, I should switch that back on. So now you see here 3 skyrmions, 2 skyrmions, 1 skyrmion. That also is commensurate with the geometry. And so they also don't move, they're fixed. And if you have 3 skyrmions, they're also relatively happy. But for instance, if we look at 7 or 8 skyrmions, they're super unhappy because they don't know how to arrange themselves, and they keep on moving around the whole time. And so this we actually quantified by the mean square displacement as a function of time. And we see that the arrangements which are commensurate with the geometry, which are 10 skyrmions, 6 skyrmions, 3 skyrmions, and 1, they actually saturate in the mean square displacement quickly. But the others, so 2, 4, 5, 7, 8, and 9, they actually continue to increase because they never find the equilibrium position easily. And this was published also a couple of weeks ago. All right, so my 45 minutes are up. So here's the most important slide. So this is all the people that did their work. So this is what we should typically look like. And I should highlight the number of key people that have contributed to this work. So Kläui, who started all the work on the dynamics of the skyrmions with spin orbitals, Nico Kerber on the ultra-fast chiral work, Jakub Sasvorka, who pioneered a lot of the thermal dynamics, Dong-Soo Han on the 3D spin structures, Kyujin Lee, Yu King Ge, and Klaus Raab, Andrea Lucia, Rob Reeve, and a lot of other people working on various aspects of the Skermion interactions, and also the theory colleagues, which is Martin Brems, Jan Rothel, Florian Dittrich, Jacobs, in the group of Peter Wirnau. And most of the work was started with Felix Bittner a long time ago. And I acknowledge in particular my permanent staff scientist, Gerd Jakob, Martin Jordan, our visiting research professor Hartmut Zabel, and Peter Wirnau for the theory. And now at the moment, we still look a little bit like that, but things are going uphill. So I've been teaching in person, so I'm very happy again this semester. And we also had great collaborations with people at MIT, in Konstanz, LBL, in Leuven, sorry, actually in Ghent, not Leuven, that's my mistake, PSI, at the Max Planck Institute and Bessie in Konstanz, Mainz, as well as the 3D Magic Consortium with Stefan Bügel, Rafael Dembakowski, Theo Rasing, Christian Good for the scattering in Siegen, as well as Oleg Tretiakov, Koji Sato in Sendai, and now Oleg is in Sydney. Nothing would work without the funding. In particular, I acknowledge support by these organizations, particularly the 3D Magic ERC grant, as well as Material Science in Mainz and our Collaborative Research Center. And so to sum it up, so I hope I've shown you today that DMI stabilizes chiral spin structures with defined topology, both in metals and insulators and in 2D and 3D. Here are the papers. Skirmian motion due to spin orbitals has been realized, and we have completely reproducible 10 billion motions, and we have identified the origin of the Skirmion Hall angle. Here are the papers about that. We've shown thermally induced anisotropic diffusion that can be used for non-conventional logic, both stochastic logic as well as token-based Brownian computing. Again, here are the paper, including our recent archive work. And Skirmion interactions, lattice phases, and phase transitions have been studied in 2D. Here are the 3 main papers that we've been working on in that field. And if you're interested and new, I just encourage you to have a look at these 2 reviews. Also, if you're interested in joining us, we have open positions. So just send me an email. And with that, I thank you for your attention, and I'm looking forward to the discussion.
Thank you very much for this interesting talk. We can use the reactions buttons to thank the speaker. And this talk is open for questions. If you're on Zoom, please raise your hand. And if you're watching this on Twitch, just type your questions in the chat box. Oleg, please go ahead with your first question.
Hi, Mathias.
Hey,
nice
Oleg.
talk. A long time no see. Well, so I have a question about the last part, Skirmion interactions, lattices, and phase transitions. So it reminded me a little bit about the activity in the artificial spin-ice community, where people were trying to reach spin-ice phases by making them in micron-sized sort of islands, acting as microscopic spins. So here you have fairly big skyrmions. They're uneven, their sizes are different, as one can see from your figures. And presumably they're also acted upon by various pinning centers and disorder in the substrate or whatnot, which would presumably preclude the formation of perfect crystals and disrupt the formation of even hexatic phase and so on. Can you comment on that?
Absolutely. So yeah, I mean, of course, you're correct. We are working in real crystals. Real crystals have real defects, and this is correct. However, it turns out that the skyrmions that we've been looking at, the optimized skyrmions, have a relatively uniform size distribution, because otherwise we would not be able to get to this hexatic phase at least. And we also have some indications that you can get to the solid phase as well. So this essentially it's a material science battle. But of course, there are always the odd defect, and you can actually see inhomogeneous condensation. You see the defects acting as condensation sites, and then you have grains growing. And now something we've been looking at how to actually get rid of the grain boundaries by shaking the system, for instance. But what I find really exciting about this is that you can actually see the position of every atom, artificial atom, every skyrmion, and at every moment in time, so you have the full information on the phase transition. And I think that is, at least from my perspective, rather unique and rather exciting. But absolutely, we have defects and we don't have perfect crystals, but on certain areas, I would say we actually see that over, let's say, the 100 times 100 skyrmions, we see as good ordering as we can resolve. So that this psi 6 is very close to 1.
Thank you.
The second question, Smriti, please go ahead, unmute and ask your question.
Hi, so I'm Smriti from India. First of all, I would like to appreciate on your talk. It was really amazing, and I had good insight on skyrmions. Sir, I have a question related to the manipulation in Skermion that we can do with anti-dot lattices. Can you comment on this thing?
Yes, I mean, essentially, as I showed in this last slide here, geometrical confinement will have a strong effect on the Skirmion positions. And whether you pattern your structure into disks, squares, whatever, I mean, this was all done here in this paper, or whether you take out something, have anti-dots, absolutely, this will affect the ordering. So by patterning appropriate anti-dot positions, you can artificially have the lattice and have an artificial lattice spacing that you want. So absolutely, that we have not done, but that's absolutely feasible. And then, of course, in this artificial lattice, you have a lattice spacing that is not anymore set by the Skirmion interaction potential, as in our case, but by the spacing of your antidots.
Yes, sir. I got your point. Thank you.
All right.
Great. Do you have other question? So it looks like there's a question in the chat. I'm just going to read it to you. How much do you see the Skirmion deformation effects, including the domain wall and shape, as well as Skirmion-Skirmion interactions significantly affecting the design of shufflers and token-based computing devices? Can this be mitigated, for example, by larger racetracks and smaller Skirmion densities? But that would then influence scalability.
Mm-hmm. Yes, it's a valid question. I mean, the Skermion deformation that we have investigated for this Skermion Hall effect primarily occurs when we drive the system very hard, when we drive at very high velocities. That's when this happens. But indeed, it sets an upper limit for the speed of the Skermions, which you can use. They tend to blow up at very high speeds. For the Skirmion reshuffle and all the non-conventional logic that occurs on the thermodynamics scale, this is much less of an issue. So there, the Skirmions are not driven very strongly. So as long as you don't have defects, they don't tend to deform much within the resolution of our imaging. But yes, for the racetrack, this is a big issue, and the way around it would be to either increase the rigidity of the Skirmion, so it's by having higher DMI, or using these synthetic antiferromagnetic Skirmions, or antiferromagnetic Skirmions where you have no deformation. So that's another way around it. But yes, it's absolutely a valid comment.
Thank you. And Kirill, please go ahead.
Yes, thanks. And thanks, Mathias, for the great talk. I have a quick question about this example where you show the interaction of the Skirmions with each other and with a wall.
Yeah.
So naively, it kind of seems like it should be something similar to the image charge interaction, that if you have a wall, the Skirmion interacts with its mirror image, so you expect the potential to be approximately the same for the double the distance, and it looked like it seemed kind of like that, but not quite. Do you have any comment on that?
I think it's a bit more complex than that, because I mean we're now looking at that in more detail, and we have more results that are coming out. Now the Skirmions, when they have a large distance, they primarily interact dipolar, and then I think your intuition is completely correct. But if you get closer, they start to touch on the domain walls where you get exchange interaction. And that then leads also to the simple approximation of an exponential or simple power law breaking down. So I think at the moment we're trying to find out, by varying the magnetic parameters, if these interaction potentials are somehow universal, or if they, to what extent they depend on the magnetic properties. So for instance, on the size of the Skirmion. I mean, this sigma, of course, is just the diameter, but there's this prefactor here. Is that depend on the size? Does it depend on the domain wall width and all these type of things? Yeah, but at least I was already very surprised that there's such a big difference. It really means that essentially if you have an edge and you miss material on the other side, that generates a stray field, that makes a huge difference compared to having a second Skirmion that also generates a stray field. Mm-hmm. Maybe for you, for a smart guy like you, this was obvious, but for me, this was surprising.
Yeah, in fact, I did mean that the interaction should be like a power law in the literal sense of an image chart, but in the sense that if you have a wall with a proper boundary condition, the configuration on one side can be the same as if you have two Skirmions in an infinite material. I mean, there may be differences depending on what happens at the interface, and indeed like the demag fields at the edge can contribute. But here it does look like the curves look very similar, with maybe just the rescaling of the distance.
No, actually, the prefactor is different. So the prefactor really is different. So it's not just the sigma, not just the effective diameter. So that I think is quite important, that this is outside the error bars different. And maybe one more thing that we also realize is when we push skyrmions very hard towards the edge, they start to deform. And that's obviously not covered by this simple effective potential picture, that assumes a constant spin structure. So they get elongated. So if you push them very strongly towards the edge of the sample, they start to turn into ellipses, and that leads to behavior that is not captured by this model.
But shouldn't it be the same when you have two skyrmions interacting?
Oh, absolutely. Yeah, absolutely. We just don't know how to put two skyrmions to make them push next to each other, too closely. It's easier to push a single skyrmion to the edge than have two skyrmions, get intimate.
Right. Okay. Thank you.
Okay.
I think Alexei has a question.
Alexei, please go ahead.
Thank you for a very nice talk. I have a question about these transitions, Skirmion transitions to this liquid phase and so on. So how do you actually detect the position of the phase transition? And can you just, do we really need to look at them, or you calculate some kind of correlation function?
So what we do is, we calculate.
Could be useful, or.
So what we do is we look at the spatial correlation function, and we fit the spatial correlation function, and we see if this fit is an exponential or an algebraic. And that essentially gives us the difference between liquid and hexatic phase. So that's a robust way. The problem is, in order to do that, you need to go to many, many neighbors. So you need to go to very large systems. Here they go to, like 20, 30 times 30 Skermion, so you need to have a very large field of view, and you do a huge amount of work. And also the other problem is that you need to wait for a long time until it's equilibrized. I mean, we know that for phase transitions, you get critical slowing down. So it just takes for ages until that happens. But that's what you do. I mean, that's also what was in the theory suggested, that one can look at the difference between the exponential and the algebraic decay. Now, there is a second parameter that you can look at, which is a bit easier to look at, which was identified that just the absolute value of the psi6, if that is the hexagonal ordering, the hexagonal order parameter, if that is larger than about 0.7, then it tends to also be in the hexatic phase. And that's a bit quicker to do, but it's not as clear and not as well-founded theoretically. But these are the two things that we look at. So the absolute value of the local hexagonal orientational order parameter, or looking at the spatial, the decay of the spatial correlation function.
And are finite size effects here known?
No, and we've looked at them, and yes, I mean, we see that's all super secret, so I'm going to tell this here so no one listens. I mean, we are now looking, of course, exactly what happens, and we find that if you make it finite size, we have nucleation at the edges, heterogeneous nucleation, all this type of stuff. That's what we're looking at right now. Yeah, so you see, for instance, that the ordering is improved at the edges of a sample where the edge helps the ordering, and the crystallization sets in at the edge and then moves in towards the center and all that type of stuff. So please, no one do it.
what I mean, finite size effects, your sample is also finite always, even.
Yeah, but it's pretty infinite for us. I mean, we're looking at the square centimeter, and the Skermion is a micron, so it's really quite a lot of Skermions in our sample.
Oh, I see. Okay.
Yeah, so I think that's less an effect. But I mean, what we did is, I showed this in this previous interaction potential work, where we actually looked at this bar to look at the Skirmion, and the Skermion here, this one. Ah, shit. This one here. And there we see exactly what I just told you as a super secret. There, the edges, they actually help the nucleation of the crystallites. And then, you get effects of heterogeneous nucleation of such a hexatic phase. And you can follow that in time and all these type of nice things.
But are you expecting also some other effects, such as maybe specific heat
Yeah, that's funny. Actually, I had this
maybe
question.
susceptibility.
I had this question. Yes, I mean, yes, but I think it's tiny. I think the entropy of the Skermions is very small compared to everything else. So yes, I think qualitatively, yes. I think quantitatively, it's going to be tough.
Okay, I see. So that's not useful. Okay, I see. Thank you.
I mean, that's my gut feeling. I mean, I haven't done the calculations, but I think it's the entropy of the system of a Skirmion is small.
But yeah, if such type of phase transitions are known, it's probably there are some theoretical predictions. So, but
yeah, I mean, there's, I mean, obviously, 2D phase transitions, I was too ignorant. There's good reason that Koslitz and Thalus got the Nobel Prize, and there's quite a bit of literature, and they've done a lot of exciting work. And, I just need to read up. And
but at least in Koslitz-Thalus transition, there is still some peak in specific.
Yes, yeah, but again,
it's
it depends.
A little bit later, but still, it is there.
That's correct, but you need to check in order to be able to measure that. You need to have, this is all dominated by phonons. I mean, the magnetic systems the Skermion system has a tiny contribution. So you would have to have some way to identify this, like from the random motion of the Skermions, rather than trying to measure absolute values. I mean, also the Skermions, that's maybe one thing I completely forgot to say. What is also very exciting is that the Skermions are really 2D. They're 2D because they're 1 nanometer thick, but 1,000 nanometers wide. So they're as 2D as it gets. It's much better than all the colloidal stuff that has been done. And colloids previously had spheres, micron-sized spheres, and they could jump on top of each other and have all this type of also 3D that are not perfectly next to each other, but slight angle that leaves lots of artifacts. But here it's super 2D. It's as 2D as it gets.
I see. Okay. I see. Looks very nice.
Okay, great. Do we have any other question? I don't see a question on Twitch. Looks like we are out of question at this moment. Okay, so we'll have another private discussion right after this. So if you want to have more discussions, please stay. At this moment, I want to thank the speaker again, and we're gonna turn off the recording and the online streaming.